Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour.
Hello everyone, and welcome back to a new episode of On Air Actual Rocket Science. During the duration of this podcast, which is organized by the Student Council of Aerospace and Geodesy, we will be interviewing the professors of our department and dig deeper into their fields of expertise. I'm Greta, an aerospace engineering student.
And I'm Phil, I'm a geodesy student.
Please welcome Professor Christoph Holst. Thank you very much for joining us today.
Thank you very much for having me here.
So you are the head of the Engineering Geodesy chair here at TUM. Would you maybe like to introduce yourself?
Okay, so I'm Christoph Holst. I'm here at TU Munich since 2 years. I'm coming from Bonn originally, and I overtook this chair 2 years ago, and now I'm trying to introduce new stuff, new methods, new applications to all the interesting students.
Very nice. So as usual, we would like to start off our episode with a little icebreaker game called This or That. It's very simple. We will give you 2 options and you will have to choose whichever one you prefer.
So, as the first questions, would you prefer a holiday in the mountains or rather at the seaside?
Mountains.
Freelancing or teaching?
Teaching.
Measuring in the field or working with data in the office?
I would prefer to work in the office.
And last but not least, probably the toughest one, laser scanners or total station?
Quite easy, laser scanners.
Okay. All right. So as mentioned before, you are the head of the Geodesy, Engineering Geodesy chair at TUM. And you studied geodesy and geoinformation at both bachelor's and master's level at the University of Bonn. 2015, you concluded a PhD with focus on laser scans. And in 2021, you eventually received your professorship here at TUM. Now, as we can see, your biggest passion or one of your biggest passions is definitely geodesy. And we were wondering, has it always been this way or did you have different career plans as a child?
Well, I always liked math, to do the calculation and to do some applied mathematics with really applications that are relevant for people. So I'd always like to do something with math. At first, I'd rather like to be a math teacher or do something in this direction. And the focus on geodesy actually started not so far away from my exams at school. So it was a quite late decision to do this.
Mm-hmm. And why precisely did you decide geodesy and geoinformation? Like, let's say, what was your inspiration?
Well, I knew the topic quite well from my father, who was a geodesist. And I knew some parts of this discipline, so how to measure in the outside, how to do practical field work. This was what he really did. And I didn't like this. I really thought, no, this is not what I want to do. But I liked the math behind and what the theory is behind. And then I got to know what is also in this field and what the discipline is based on. And it's not just this field work. And so I realized that this is really what I would like to do. So applied mathematics. And this is when I thought, okay, I could choose this, although my father is already a geodesist.
Okay, that's very interesting. So talking about geodesy, I bet most of the people out there have heard the word geodesy at least once in their life, but I'm pretty sure only the fewest know what it really is about. So could you maybe give us your personal definition of geodesy?
Okay, yeah, this is really the problem, that the people really interact with geodesy, but they don't know this because the discipline is not well known. So geodesy, we can define as the discipline of measuring and displaying the Earth in its complete structure and its complete geometry, but also with parts of the Earth. So we have sensors, we use sensors, different sensor systems, where we want to survey the surrounding and its local geometry, but also like continents or regional aspects like countries. and we want to find out what the geometry is, how the relations are between different points, and we want to analyze and display this. So what changes on the Earth? What is the relation between points in Europe or in America, and how is the relation changing? Or how are buildings behaving, or the landscape? How is this shaping in sense of climate change? So this is all relevant in geodesy, and this is all one aspect. But I have to admit that this is a large field that is not easy to explain in its full dimensionality. So this is why we have a clear problem that the science of geodesy is not well known, as you said.
And what about geoinformation? Let's say, what is
geoinformation is the part of my aspect is I want to measure stuff. I want to measure the geometry, and then afterwards we need to display this geometry. We need to map this in aspects of cartography, but also in geoinformation systems. So we have digital systems of displaying the changes of the Earth and also the Earth itself. So the discipline is sometimes called only geodesy and sometimes called geodesy and geoinformation, as also the study program here.
Very interesting. And another very interesting fact about you is that between 2012 and 2021, you did quite a few activities as freelancer. And such as the evaluation of geodetic networks and the development for alignment of traveling band screens. Now, I was wondering, how did you even come in contact with such a freelancing activity, and how can we imagine such an activity to take place?
Okay, well, this activity was done as a freelancer, but it was still related to university. So it was, parts of it I was doing by myself, and parts of it with connections with people also at university. And our discipline, at least the engineering geodesy, is quite related to really practical applications. So we consider always questions, or let's say we always try to solve problems that really exist in reality. So we are always applied to practical questions, and we want to find out practical solutions. And this can concern like small machines that need to be aligned to be working fully, or this could be that there is a company that wants to find out if a facility is positioned well and stable, or if there's some movement in this facility. And here we evaluate or develop methods and use sensor systems to solve those problems. So this is really always adapted to current questions that may be resolved out of industry or something. And this is how this started, that people came to us and asked, can you help us in finding a solution or in evaluating if an already existing solution is working properly? And there we have, I try to evaluate this current situations and then give advice on how this works.
And in 2022, you also worked at the DVW, Deutscher Verein für Vermessungen, which is an association that has the focus on promoting science and technology. And you were the head of the working group for mobile and autonomous systems. And what was your role in it, and what did this group work on?
Okay, well, this group just started.
Oh,
there was the DVW is the representation of the geodesists in Germany, or let's say we have different representations, but this is the largest one, and they have different working groups, and the task of those working groups is to combine or to collaborate with different people from research, from science, but also from industry and from administration, that are working on a specific topic, as here mobile and autonomous sensor systems. And we just formed this group, and we would like to interact with each other, so to find out or to communicate different aspects of mobile sensor systems so that we are on the same level, because there are currently several research questions that are also relevant for industry and also for the persons working in the field. regarding those mobile sensor systems. And our task is now to interchange our knowledge, our experiences, and then also to bring those experiences into the large field of geodetic practitioners. So we will give seminars, we will give white papers, we will maybe make a podcast or something like this to promote our knowledge for the working people in geodesy, so that they are also up to date.
Great. So before we dive in any of your research, of your projects, I think it would be nice for those who are new to geodesy to maybe give a little explanation or overview what laser scan or total station or level specifically is, how they differentiate and how they work or are applied or used.
Okay. So we use and explain and develop different kinds of sensor systems or instruments, we call them. And they are all existing because they map different kind of geometric aspects in the surroundings. So if we talk about levels, for example, they derive height changes. So if we want to derive really accurate height changes with an accuracy of some millimeters or better, we use instruments that are called levels that determine just a solely one-dimensional height change over longer distances. We can derive height changes if we step-by-step measure of many kilometers. This is how we get our German really accurate height system. And then we have different sensors that are called total stations. They measure angles and distances to derive three-dimensional coordinates. So not only heights, but three-dimensional coordinates, so that we get a planar coordinate and also a height, so in 3 dimensions. And this is based upon some instruments that maybe you all know, because they can be seen on construction sites. They can be seen when a house is built or when a street is built, because they really determine 3D coordinates that we need in all the construction processes and also other applications. They exist since decades. There is a development in them, but they exist already since many years. And then there is a rather new topic, let's say, it's really in the field work since 10 to 15 years. This is terrestrial laser scanning. And they are just instruments that give us the ability to map everything that is around. So to acquire something similar to a 3D model of the surrounding just by pressing one button, and in really short time get every information about geometry in the surrounding. And this really made a large step in the geodetic field and research, and also in the field work, so that we can solve many more tasks since we have such variety of sensors.
Perfect. Well, coming from those devices and methods, you have been involved in multiple projects, one of them being the deformation analysis of bridges or buildings, dams. As most of you know, throughout the time or influence of the forces of nature, those move. How is that working, and what exactly are you doing in this field?
Okay. To start, well, this is a really important topic. We have thousands of water dams in Germany and all over the world that need to be monitored to assure their work and to assure that they are safe. We have thousands of bridges that need to be monitored because they don't work properly. We know this. There are thousands of bridges in the world that need to be replaced or maybe repaired in the next years and decades. So this is really something that is a focus in engineering geodesy, to monitor something like this. And here we are working on how to improve the accuracy in monitoring something like this. So how to find out even smaller changes, because this is relevant. Even the sooner we can detect changes, the sooner we can do something against this. So we are working on the one side and increasing the accuracy to find it out sooner. On the other side, we have new sensor systems like the laser scanning that help us in analyzing the complete structure. If we talk about total stations, we just can measure individual points. So we go to a water dam or a bridge and measure just, let's say, 10 to 20 points on the bridge to say if something is moving. But now, since we have sensor systems that are able to acquire the complete surrounding in a really short time, we have new possibilities to monitor and to find out earlier and to say something about the complete object. And this really is a really big step that many people are working on, and this is also one aspect that I'm working on in my research projects, to use this new technology for better analysis of the changing infrastructure.
I see. What are the challenges that you're facing in those projects or that you're dealing with?
Well, the challenges are the sensor systems bring really advantages if we talk about laser scanning. But we also have lots of new problems. If we are talking of a sensor that just measures on the surface itself, so let's assume we want to monitor a bridge, or let's say a water dam. The water dam is constructed maybe out of individual stones. And if we measure on those stones directly with a laser beam, because this is laser-based system, then the laser beam is reflected in different directions. And this leads to errors in the point cloud, in the measurement product that we need to analyze. And if we really want to find out if the water dam moves, we need to separate those errors from the real deformation. And this brings in methods that we need to develop, because this is something new, to be really sure about this. Because in the end, what we always like to do is we want to say, okay, I am with 99% sure that there is something happening. If I'm not sure with this amount, then maybe the bridge is not closed, because the civil engineers say, okay, if he's just for 50% sure, why should we close this? And this is a problem, so we need to be really sure. We need to find out early if the deformations exist, and we need to find out on the complete structure if there is any deformation. And to answer all those questions or to address all those topics, we need to find new methods and develop them.
How do you differentiate those deformations compared to uncertainties of the measurement?
Well, there is a clear defined statistical process that is known since several years, since the startups of the deformation analysis. It's just a statistical test trying to find out if the measurement errors that we are gaining are, let's say in easy words, is smaller or larger than the change in the coordinates between two epochs that we measure the object in. And if the measurement noise is larger, then we cannot be sure that it's real deformation. But if the measurement errors are smaller, then we can separate those two aspects and say, okay, this is really deformation. But the problem is here to know the uncertainty structure, and this is where we're working on, because this is quite complex.
Is that the field that you're personally working on, or are you more focused on the measurements themselves?
No, we are focused on both aspects. So we are focused on how to improve the measurements, how to perform the measurements, but also how to analyze the measurements in sense of knowing in the best way what part of the measurements is really the structure, the geometry, and what part of the measurements is errors, in sense of random errors, systematic errors, or outliers.
Is that only only you as a professor involved, or is that the entire chair or the entire team?
Well, we have in my chair, I'm involved in different research projects, and part of several research projects is in different ways to perform measurements and to analyze the uncertainty. So many people are involved in this. This is, let's say, also a key competence of engineering geodesy, to acquire measurements and to be really sure about the stochastic properties of the measurements that are gained.
I see. Well, as we found out, you're not only involved into surveillance of structures, but also into alpine surveillance, or the chair at least has been. What can you tell us about that? What are the differences to the surveillance of buildings, and how is that going along?
So the difference between structures, buildings, and environmental objects?
Yes.
Well, let's say when we try to find out measurement concepts to solve questions, to solve tasks, we are always collaborating with the people that are really into the object itself, that whose key competence is the object. Let's say if we monitor buildings, we collaborate with civil engineers. If we want to monitor landslides, for example, so moving slopes, we collaborate with environmental engineers or geologists, because we always need, if we want to find a solution for a question, we always need to collaborate with the persons that really know the best about the structure we want to analyze. So this is the basis. So we need to collaborate with the people knowing about if we talk about environmental objects, knowing about the geology of the landslide, for example, knowing about the soil and the consistence of all this stuff. The difference is that we then need to adapt our systems, our knowledge to this problem that we are right now solving. So for a landslide, compared to a water dam, for example, we need to first find out where is the landslide ending. So where is the border of the landslide? So at which position do we have a stability, and at which position do we still have a movement of the landslide? This is maybe more easy to find out if we talk about a water dam, because it's a constructed water dam. But for a landslide, we need to find out this previously. So it's rather a problem also of detection, where something happens and where not. And then there are also some other stuffs that are related to the object that we need to consider.
Comparing the two parts of the civilians, would you say there are different challenges besides limiting the area of influence?
Yeah, obviously. Well, if we want to monitor some natural object, then we have a surface, for example, that is not dedicated to measure on. So we know a building is constructed maybe out of stone, and we know the reflectance of stone better than we know the reflectance of grass that we would like to measure on, or soil. So we have more problems, or let's say it's more advancing if we have objects that are made by the earth and not made by the people.
I see.
Sorry, can I just interrupt real quick, because you talked about the bridges, and I just have a question about that. How exactly do you measure such changes? Like when talking about bridges, just I cannot imagine how the setup looks like.
Well, there could be lots of different possibilities. One possibility could be I just position a measurement system underneath the bridge, and then I measure on the ground side of the bridge. Maybe I position a reflector there and then I measure repeatedly this reflector. And then if I just stand beneath the reflector, I can just, by distance changes, I can find out if the reflector moves in height or not. So then I could find out, for example, vibrations. If a truck goes over the bridge, I would find out that the bridge deflects a bit. So this would be quite easy. But there are also solutions where I just place some sensors on the bridge, like an accelerometer sensor or some inertial measurement unit, and then this by itself measures changes in the vibration by measuring acceleration or orientation changes, for example.
And is it important that let's say the positions where you place the sensors are always exactly the same? Let's say if you want to monitor the change of a bridge over the years?
Well, this if it is the same position, I have some advantages, because then I can rely on the fact that I have the same behavior at the same position, and then I can analyze it more easily. But in reality, we often have the problem that we have different positions, or that we have sensors like the laser scanner that will not measure at the same position, but that will measure the surface at some arbitrary other position. And then we need to relate this to each other by a geometric model. And then to find a model that represents this, maybe also in contact with the civil engineers that have a finite element model, this is then the task, which is more advancing, but which is also then better for a full interpretation of the behavior of the bridge.
Makes sense.
Do you have maybe an example of a real-life practice where either landscape or building civilians has been taking place that TUM or you yourself has been involved in?
Yeah, well, in research, we are really monitor water dams and compare the results with a local administration that is responsible for doing this, and we interact with them and give them advice how new sensor technologies could be used to monitor it with better interpretation. Then we are involved in some projects where we monitor like the mountain Hochvogel and other mountains, where we indeed collaborate with geologists and other people, and where we have results seeing that there is a gap in the top of the hill, leading to that will lead at some point to a rockfall with a large magnitude, and this is something where we are involved in.
Maybe let's get a bit into more detail. Could you, I don't know if it's too complicated to explain in words, but how exactly does, for instance, a laser scanner work, if it's manageable to explain that?
I hope I can manage it. It's what I need to do several times a year. So it's a sensor system that consists of different aspects. Well, we could start with, there's a laser beam that is shot in different directions of the environment. So this laser beam is shot on the surface like a wall, and then the wall reflects this laser beam. And then the sensor itself measures the time of traveling of this laser beam. And by this time of traveling, we get the distance. And then, since the laser beam is not only shot in one direction, but in different directions, we get also, on top of the distance, we get the angular measurements, and we divide here between an angle that is only concerning the horizontal plane, so an horizontal angle, and the second one, the vertical plane, the vertical angle. And this is achieved by a rotating mirror that is included in the scanner. So the laser beam that is shot on this rotating mirror is deflected in different directions because the mirror rotates vertically and also horizontally. And then we have 3 measurements: the vertical angle, the horizontal angle, and the distance. And out of this, we can derive 3D-dimensional coordinates, rectangular.
Very nice. And in the beginning, we also mentioned the total station. How does that work more in detail?
The mechanical parts are quite similar. So we measure the same stuff, but we measure not with a rotating mirror, but we point at certain aspects in the surrounding. So I would look through the total station and point one point in the corner. And then I just measure exactly this point in the corner. So it's manually. There's also aspects of making this more automatic, this process, but I don't measure everything surrounding me, just individual points.
Due to technical reasons, we now have to take a short break, and please enjoy the Marius 60 seconds of politics.
The Council of Student Representatives, FSR, is a large committee where all student councils get together to discuss all matters that affect the life of the students of TUM. To achieve this, it elects members to take executive positions. These executives form the General Student Council of TUM, called ASTA. Examples of those positions are the representatives in the Senate or Board of Study and Teaching. Other representations are outside of the university, such as toward the Munich public transport companies or the Conference of Student Councils in Bavaria. Also, the large student parties and festivals, such as ESP, Unity, Tunix, Organics, are organized by people that were sent from the Council of Student Representatives. The voting members of this committee are elected in the yearly university elections, but all students of TUM are welcome to join the meetings. If you're interested, best contact your student council's university politics team.
All right, so coming back to associations, another very interesting association that you have worked with is the Laser Antenna Scanning Surface Instrument in West Virginia at the Green Banks Observatory. And now I'm interested in knowing, what does this association tackle and how does the observatory link to it?
Well, this is something where the responsibilities contacted me about, I think, 3 years ago, because they want to tackle the problem that they want to measure with a really large antenna with a diameter of something like 100 meters, signals from space. And the problem is that if we have an antenna of this size, then the antenna is not stable in its geometry, because we have the sunshine and we have wind and other things that lead the geometry to change during time. And this is, they came to me because I am working in this field since the start of my PhD. This was one of my first research projects where I analyzed how much radio telescope changes its geometry depending on its orientation, or maybe also depending on sunshine. And we are talking here, with a size of 100 meters, we are talking about changes of some millimeters. So it's a really small change, but this deteriorates the signals from space and gives, for example, a shift in the signal processing. And this shift leads to wrong interpretations, so we need to correct this shift, and therefore we need to know the deformation on the dish, and this we need somehow to measure. And those people from the LASSI group, how it is called, contacted me and asked for advice how they could do this. And then there was some interaction, and they are now measuring the signals, and also have a concept of how to calibrate this antenna depending on the sunshine.
That's very interesting. I would have never imagined that such small changes could actually have major impact on...
Where I come from, this is dedicated to the VLBI, which is the Very Long Baseline Interferometry. And this is one aspect of space geodesy. And here we are trying to install a network of coordinates all over the Earth, which we call then ITRF, International Terrestrial Reference Frame. And this is the basis also for aerospace and everything, to have precise points on Earth. And those points, or the orientation of the Earth that we also need to know, and the rotation rate, depends on measurements with radio telescopes. And the aim is of these coordinates to have an accuracy of beneath 1 millimeter. And to gain this, we also need to know the corrections that are due to the shape deformations of the main reflectors of the radio telescopes.
Very nice.
Exciting. So to bring another or maybe a last example of real-life practice of geodesy, we know that you have been involved in the FSLRG project, Civilians project. And what is the project about, and how were you involved? And most importantly, how does geodesy come to a real-life practice here?
Okay, well, this FSLRG project is a project where the geodesists collaborate with the people from agriculture. So, to be honest, my part was really not mentionable in this project. But I was working for the chair hosting this project right now. And the idea is that we want to have a sustainable agriculture where we use robot systems that automatically go to the field and make the complete process of harvesting, of managing the agricultural field automatically. So therefore we need robots that need to know in each situation where they are. And they need to collaborate with each other. And therefore we need position information, which is based upon GNSS, which is based upon total stations or something else. And this part of positioning the systems and interacting the systems with each other, this is the part where geodesy is involved.
And so how does the implementation of robots lead to a more sustainable crop production?
Okay, well, if we have automatic robots that manage the crop field, then we could, for example, use robots that automatically detect weed and that destroy this weed by some fire or by some punch. That is also one system. So we mechanically destroy the weed so that we do not need to use so much pesticides, which is then better for the groundwater and so on. So this is the aspect of sustainability.
Okay, that makes sense. Yeah, thanks.
So we see that geodesy has a lot of application. To finish on though, I do have a last technical question. We talked earlier about the total station, the laser scan, and in the end they have somewhat similar use, the one being more precise, the other one measuring a bigger amount or a larger amount of points. The question that stays left in the room is whether you believe that the laser scan will at some point be so precise that it will replace the total station.
No, I don't think so. We have really different applications that we use those sensor systems to. If we really want to find out in the large area what happens there, if we want to document changes, let's say in construction sites, if we want to document what happened during a day, in sense of a construction process monitoring, then we need aerial information. We need to know what is happening everywhere, and the precision is not so important, let's say this. But we also have many applications where we, at specific individual points, need to know the best information that we can get. So we need to know with a really high precision what is happening there. Maybe if we talk about vibrations of a machine, or if we talk about buildings where specific structures are relevant, not the complete structure, but specific locations, then we need to have measurement systems that can precisely get this information, and therefore we use total stations. So I see different developments where all they are going, but I don't see that there is a replacement of a total station by maybe a laser scanner or something else.
So you don't believe that the laser scanner can have this preciseness that a total station would have?
No, because this is the problem is physics. We measure with a laser on some surface. And there we have physical problems that we need to analyze. But if we bring our own surface with a total station, we measure on prisms that we bring by ourselves. And those prisms have one reason that they are existing. They have the best surface for the laser beam to be reflected. And if we measure just on grass on a wall, they have different purposes, but not at all that the laser beam is well reflected. So we have physical limitations, meaning that we cannot get this precise with a laser scanner compared to a total station, measuring on prisms.
I think that will lead us to our last or final question of today, a very classic one. Besides your research, you obviously are a professor, and so the last question that leaves out is possibly the one for future or current students. What advice would you give them for somebody who considers going into geodesy, or even for somebody who is already studying geodesy?
Well, one advice could be studying is not always easy, as everybody knows. So you really have to keep on track. You really have to see the aim that you have, that you connect your study with. So what do you want to do in the end? This is not always related to what you currently learn at that day or in this week in your study, but you have a clear aim, or you should have a clear aim of what you want to do with it afterwards. And this is so interesting. There are so cool topics that you could do afterwards. So stick to the study and always think of your future that you could reach, instead of thinking that this week is not as you expected it to be, or you learn something where you think, okay, might not be that relevant that you thought before of.
For the students in the field, how do you think that classes or studying might change in the future, content-wise?
Well, we always have what I am always asking myself is what to change from content, and we always have the basics that relate to physics or mathematics that just remain the same, and that the students need to know to be able to understand what happens afterwards. But on the other side, we have more and more challenging sensors, multi-sensor systems that interact with each other, that you always also need to understand what happens there. So this is always the question that I have, okay, how much should I stick to the basics? How much should I get into the developments? And what do I have to cut at some point? Because the amount of lectures that I give will not increase in the study program. So this is always a changing field. And I try really to give you the basics and to really stick up to date to show you what sensor systems exist in the field. What are you using afterwards in your study? So that the study is not decoupled from the real life afterwards. And so there will be some developments in this field. There will be also some new technology developments. But the basis of all, the understanding about the math behind, at least most of the parts are all related to geometry, and this will not change, so the basis will remain the same with some adaptations to new developments.
I see. Well, thank you very much.
Yeah, so thank you very much for joining us today. It was a great chat. And to our listeners, thank you very much for tuning in. And most importantly, stay buckled in for the next episode of On Air, Actually Rocket Science.
See ya.
Bye.